muscle, and muscle's conductivity is more in this direction. So the signal propagates more in this layer, in this plane, and there is minimal signal propagation in this plane. So if you look at this, though the electrodes in the muscle, they give out isotropic radiation pattern, the resulting radiation is totally different from what we want. So the array factor, that is the net signals that we combine with all this pattern, will be more in this direction, causing interference to the neighbors. But it will be so minimal in this direction. So here, the isotropic radiation is actually creating a stronger electric field longitudinally, and if there are M implants simultaneously transmitting, this effect is going to be even more strong. So this array effect gives very low SNR at the relay. So as a result, we will be transmitting more power from the implants, causing more interference, but the SNR is going to be maintained almost in the same level. There won't be much improvement. So rather than this kind of signal propagation, we need a beam to be formed towards the relay. So how can we form this beam? When you form such beam, we should take certain factors into consideration. First, the implants should not be overloaded with more computation. The implants are already resource constrained. They cannot spend more energy in forming the beam. They can just sense the data and transmit them. That's it. They cannot do anything more. So all the computations related to the beam forming and other overload has to be done on the relay. The relay is a surface node that can be easily recharged. So we have to move all the computations to the relay, and the relay should instruct the implants to do something at a particular time. So these steps can be easily accommodated if we have CDMA for the implants transmission. The implants can transmit using some codes without understanding what the data is and without doing anything further. And the relay can use beamforming so that the relay can calculate the weights. The relay can calculate how the beamforming can be done, and it can instruct the implants to do that. So what is the advantage of this? When we have these two, the CDMA and beamforming techniques combined, the energy spent per implant will be drastically reduced. So as the number of elements increases, the energy consumed per implant will be very low, and also the relay gets a very high SNR. So you can reduce the transmit power even low, because the high SNR at the relay is already available, so you get low error rate. So the power consumption can even be reduced, and these are directional signals when you form the beam. The more directional it is, less the interference to the neighbors. So we have these advantages. So here comes the complexity. In the normal beam forming, we assume it is far field. So when a laptop is here and I am standing here as a plane, and another person standing here has another plane. So in this plane, the peak-to-peak amplitude and the phase difference is going to be constant. And when I move a step further, the peak-to-peak amplitude throughout this plane is going to be again constant, but with some reduction. So this reducing in quantity of the signal is based on the channel, and this is going to be constant, which is proportional, which is the inverse law. It can be inverse square law or it can be inverse cube law based on the n component you use for the path loss. So, by tuning the phase of the signal, you can decide where the beam is going to be. So where the constructive beam is going to align, either in this direction or in this direction, just by tuning the phase. So this is the normal beam forming. So what happens inside the body area is that, so in this frequency range, the far field is not inside the body. The far field is totally outside the body. What is this far field? So the far field is the range of communication over which you can assume the plane assumption of the wavefront, where the electrical and the magnetic fields will be totally out of phase, but they'll have a relationship maintained between them. And both of the waves will be considered together as the power, and the power will be proportional to the impedance of the air medium. So which is going to be 377 ohms. So this is constant for the air medium. So beyond this range, this is far field, and you can see they are not the E and H fields anymore, which is in the near field, but they are just the power beyond the far field area. But what happens in the near field? The E and H fields, the electric and magnetic fields, don't have a direct relationship. They are not orthogonal, and they are not going to obey the inverse law. So you cannot predict how the signal is going to be attenuated in a given medium. It is depending on the medium impedance, the circuit impedance or the medium impedance. So what happens is, the electrical field will be uniformly distributed in a heterogeneous medium like human tissue. But the magnetic field depends on the current distribution. If you have a bone, there is more loss. If you have a muscle, there is a low loss region. So the current distribution is not uniform, and so the magnetic field is not going to be uniform, it's going to vary. Whereas you have a more uniform electrical field. So the relationship between the E and H field is not direct. So in that case, in the near field, you cannot assume the plane wavefront, you can assume only the spherical wavefront, and you cannot have the power as a single factor. You have to design the E and H components separately. So this is the challenge with beamforming inside the body. So what happens here? We have the spherical wavefront. We are computing the E and H fields separately. So it is a heterogeneous tissue. We have to compute the E and H fields differently in each tissue, and then compute the overall H field at the receiver. And we have to calculate the drift in frequency and phase. So we should know what will be the resulting phase in the receiver, so that we can match it at the transmitter to have the synchronization of phase. So we have to measure the drift in frequency and phase. And when we have multiple separate elements, in normal beamforming, there will be a single transmitter with different transmitting elements. So all the transmitters are transmitting the same information. It's going to be easier for you to control the phase and the amplitude. But in this case, they are not the same nodes. There are different separate nodes, and each node have different data to be transmitted. So you have to compute the array factor, taking into account the separate elements in the array. And then you have to consider tissue safety. Beamforming is constructive combination of signals, and this constructive combination should not exceed the safety limit allowed in the tissue at any point. Be intermediate between the transmitter and receiver, the constructive combination should not exceed. That should be taken care of, and then you have to compute the array factor. So this is the difference in near field beamforming compared to the far field beamforming.
So can I interrupt you 1 second? So you are beamforming from the implants to the relay node,
Yeah.
right? So you're trying to beamform from each individual implant to the relay, right? You're not doing distributed beamforming.
So we are making it distributed later. So
Okay.
if you
But then you have to have the same data at the different implants
Yeah.
somehow. So you're transmitting the same thing. So
yeah.
So you will have to tell them how is the same data being. Are you going to cover that?
Yeah,
Yeah.
it's coming there.
So the data somehow becomes the same at multiple implants, and there's a trick that we do,
okay.
and then we apply the beamforming.
Okay.
So that will be covered in the next slide.
Okay.
So here I'm going to show you the results in the form of azimuth plane and elevation plane. So just to tell you what is an azimuth plane, if you have, this is the XY plane, so the area covered by the XY plane, that is if you have the implant here, this plane is the azimuth plane and this plane is the elevation plane. That's it. So if you want to form the beamforming in this plane, the signal should not propagate in this direction. So you have to restrict the signal like this in the azimuth plane. Whereas in the elevation plane, the plane like this, the relay is here, the implant is here. So the signal propagation should be tuned in the 90 degrees. There should not be any signal in the other direction, or there should be minimal signal in the other direction, but the maximum should be at this point, which is the 90 degrees at the elevation plane or the 0 degrees. So with this assumption, I'll show you how we set the objective. So this is the azimuth plane. This is the original signal wave which the implant propagates along the muscles. So it is distributed in this direction. After beamforming, it should be like this. So this signal has to be narrowed down like this. And this is the elevation plane. So this is the position of the relay. The relay is at 0 degrees. This is 0 degrees. So now there is minimum signal here, and at 90 degrees there is no signal. At the end of beamforming, you should have more signal at the 0 degrees. This is the objective we set for beamforming. So how are we going to do this? So we form 3 weights that will help us to create the beam. Initially, the phase match weight. So when we have different signals, when we have different transmitters, we should match their phase. So when we match the phase, we could have some more gain, which is not a combination, which is purely constructive. So to form the purely constructive, we match the phase using the channel models we had earlier, and also we measure the phase difference using the Arduino test bed I showed you before. So with those phase differences, when we match them, you can see the earlier amplitude is only 1 microwatt, but now after the phase match, we see 3.5 microwatt. So this is the gain we achieved after the phase match. The next one is the power safety weight. So we form this weight just to ensure the power received at the receiver is just enough to assure the VER as desired, and it is also not exceeding the safety limit. So this is the safety weight, and finally we have the steering weight. The steering weight is computing the amount of amplitude, the peak-to-peak amplitude, and the phase that each element should transmit in order to form the beam. So here we are computing the wave number, the exact frequency, so the frequency is central at 10 kilohertz, but we can slightly modify the frequency so that we could achieve the wave number that could form the beam. So the wave number, the peak-to-peak amplitude, and the phase. All these 3 are set with the steering weight for each and every implant separately. So with these 3 weights, when we form the beam, you can see that earlier the peak was here, now the peaks are here. So this is the azimuth plane. So in the azimuth plane, earlier the peaks are here, now the peaks are here, if you want to see in this direction. So this is after the beamforming effect. So how we do this is, the relay is computing the CDMA codes. So depending on the number of elements in the array, depending on the number of implants, the CDMA is the relay is designing the CDMA codes with a number of chips, and then it is distributing them to the nodes. So the node, the implant, combined forms the chip, spreads the data based on the CDMA codes, and then they give it to the aggregator. So there is an aggregator which is one of the implant. So we choose this aggregator for every cycle. They take turns, and then one of the implant acts as an aggregator. They sum all the codes. I'll show you the detailed step later. And then these summed codes are transmitted to the signal. So these summed codes are again given to all the individual nodes, and all the nodes will have the aggregated code value. They are not the individual implant data anymore. They all have the aggregated code value, a single code value, and then they transmit them through the tissue channel. So the relay takes them and then applies the same CDMA codes back to extract the data. So we use the Walsh codes, which has the excellent correlative properties, so that you need not synchronize the transmission from each and every implant. Even if the implant 1 transmits at one time and implant 2 transmits in the next time slot, due to the correlation properties of Walsh codes, they can be put together as an aggregated code. So this is the CDMA technique we use. And now the end-to-end procedure. So how the procedure starts is, the relay computes the CDMA codes. It computes the weight for each and every node. So the relay is the receiver. It knows the quality of the signal. It knows the channel. So based on the channel performance, it computes the weights, and then it it gives those weights along with the CDMA code to each of the implants. It also assigns the aggregator. So for each and every cycle, which implant is the aggregator will be assigned by the relay, and it also handles the communication acknowledgement back to the implant. It also does one more thing. So the instance of the forming the beam should be perfectly synchronized, so that all the implants transmit the signal at the same time. That synchronization is also performed by the relay. It tells them that exactly at this moment the beam has to be formed. So with all these instructions from the relay, the implant calculate the code words and exchange them with the implants. So the relay is sending the data from the surface to the implant, and then the implant exchanges them within the muscle tissue. So this exchange need not go to the surface. It can be handled only inside the muscle tissue. The gain of the muscle is about 90 dB to 22 dB, whereas the gain of the muscle to skin path is around 35 dB to 40 dB. So the loss is very high in the muscle to skin path. So when the implants communicate among themselves, it's going to take dramatically lower energy for this communication. So once they share data among themselves, so this is the individual code words, the individual chips, all the implants will have transmitted their code words. The aggregator has collected all the code words and put them together. And now the aggregator transmits the code word back to all the implants. So again, this will be inside the muscle path, which is the high gain path with low loss. So the implants are using very less energy to receive them. And finally, they broadcast. So based on the aggregated code, all the implants share the same data, and now they are acting as the exact array elements of the normal beam forming scenario, because they all have the same data. They just transmit the same code word to the implant, to the relay.
Okay, Meenu, but I mean, my question is, so for now to transmit every single piece of data from the different nodes, you have to share that piece of data with every other node.
Yeah.
Is that worth it?
Yeah, I'll show you this analysis.
Thanks.
So if you see the whole process, even though the relays can transmit, even though the implants can transmit their data at any time before the beam forming, they don't collide with each other. So we analyze this proposed algorithm. We analyze in terms of 5 different parameters. One is directionality. So how much is the directionality we achieve? How much is the signal deviation away from the neighbors? And then what is the processing latency? So we are having the back and forth communication. Is it worth doing? And then what is the improvement in SNR? And how will the size influence? How many number of nodes will be ideal for the scenario? And finally, the most important question, energy consumption. So we have the implant transmitting first, the aggregator transmitting next, so the implant transmitting next. So we have 3 phases of transmission from the implants. Is it really energy efficient? So we'll analyze this here. So this is the result we got after the final simulation. If you see the directionality, this is the form before beam forming, and this is the signal after beam forming. So we could, using the steering weight, we could eliminate the energy in other directions. So this is the direction in which the relay is. So this is corresponding to 0 degree here. This is the elevation plane. So in the elevation plane, the signal is degrading in other directions, and there is a peak only in the relay position. And similarly, from the azimuth direction, we have the peaks in the 2 points which are not in this longitudinal direction, which are in the transverse direction. So the directionality seems okay. So looking at the processing latency, how much time does it take for this information to finally reach from the transmitter to the receiver? So with the traffic flow of 32 bytes, so we take the 32 byte size as a reasonable size for the implant data. We don't need an exhaustive header. So with 32 byte, you can reasonably transmit the implant data. So with this size, we estimated the cycle time to be 1.3 milliseconds. So with Zigbee,